Hello and welcome again to the Theories of Everything program. I'm David Tao. Viewers, in a recent program I interviewed the director of the Quantum Computing Technology Centre at the University of New South Wales, where they're building one of the world's first quantum computers. Now, the core of this quantum computer, the technology on which it's based, involves embedding individual ions, potassium ions, in a silicon substrate. They have to be positioned extremely precisely so that they'll be able to interconnect, so that their electrons will be able to intermesh eventually perform calculations in parallel rather than serially, and therefore do calculations extremely quickly. In other words, be able to solve very, very difficult problems in a fraction of the time of normal computers. But the ability to be able to manipulate those potassium ions so precisely in that silicon substrate is the essence of this program in terms of what we call nanotechnology. This program is about the new emerging science and engineering capability, all encompassing and called nanotechnology. The term nanotechnology really refers to materials, processes that occur at the level of around about a billionth of a metre. In other words, 1,000 times more precisely, 1,000 times smaller than microprocessors, which are around about a millionth of a metre. Now, already a fair bit of work's been done at that micro level to build tiny little machines, tiny little motors that have very amazing ramifications and potential value to humans. However, getting down to the billionth of a metre starts to get us right down to that atomic level, that subatomic level, even the molecular level. Individual molecules, individual atoms. There are roughly about 10 average atoms to 1 nanometre. So you can see that is the level, that is the conceptual level that scientists are now driving at. And the reason that they're driving to get to that level is because, for example, a good example was quantum computing. Without the techniques and tools to manipulate individual atoms and be able to capitalise on their properties, the properties that physicists have been able to define mathematically and very precisely, particularly over the last 50 years, those properties such as spin, charge, etc., the essence of quantum mechanics, are now able to be transformed, taken by engineers, taken by scientists and transformed into extremely valuable products. Products, for example, that can do, again, super fast computing, super dense storage, nanoparticles that can act as very precise catalysts to facilitate complex chemical reactions, new properties of material science, for example, in cosmetics, in car paint that can change colours depending on the light. Sunscreens, for example, very tiny particles that are much more valuable in that form than in macro particle form, can deflect the sun's ultraviolet rays much more efficiently. And also in the area of not just computing and storage, processing, but in the area of sensing the environment. Because once you get to that level, the atomic level, the ability to sense anything, whether it's movement, whether it's pressure, whether it's temperature, becomes much more precise and much more sensitive. So there are major spin-offs, which is why this technology, nanotechnology, is developing at such a fast pace, why it's so important. And remember, the major driver for all of these technologies is to further develop human potential. Humans constantly are striving to develop their potential at the individual level and at the societal level. In other words, if you have computers that are smaller, therefore you can pack more devices into the same area, therefore you can do more complex calculations, for example, more complex processing, you can solve more complex problems at a lower cost. The same goes for storage. The amount of storage that we'll need to encompass all the phenomena of this planet and the universe in the near future, whether it's the sequencing of genomes or whether it's the, if you like, the sequencing of galaxies, will be just incomprehensibly almost enormous. So storage is quite critical. For example, being able to sense, as I said, the environment will be more and more important to humans. Everything that can expand our consciousness, that can expand our potential, and we want it quickly, which is again why nanotechnology is taking off at such a huge pace. But it couldn't have taken off at that pace earlier. First it needed the theoretical substrate, quantum mechanics, quantum theory, developing further, particularly over the last 20, 30 years. Then there had to be the tools developed and the techniques to take advantage of that understanding, to actually work at that physical atomic level. And these have only recently come into, been available at a reasonable capability. Atomic force microscopes, scanning tunneling microscopes, for example. These can not only image atoms, but also manipulate atoms, and this is obviously quite crucial. Chemists have always worked at these at very small levels, but they've usually worked with large numbers of molecules, thousands, millions, trillions of molecules in quite small samples, achieving new materials, polymers for example, but not being able to work at that atomic level. This was the dream of alchemists going way back, centuries back, the ability to change one element into another, lead into gold for example, but they didn't understand the structures, the atomic structures. They were able to change and create new materials, but at the electron level, at the valence level, not at the nuclei level. They were able to, chemists up till recently have only been able to manipulate elements, atoms at that electron level. But of course in recent times it's become possible to add protons, for example, add neutrons, split nuclei into various components using particle colliders, for example, and using, of course, nuclear power. Nuclear power stations have been used to create side products which are very valuable in the medical area. Products such as fluorine-18 that give off positrons, for example, and enable soft tissue images to be obtained. Now, with this capacity and this potential have been combined new tools. As I mentioned, the atomic force microscope, which consists of a tiny little cantilever with a very tiny point. The point is about 10 nanometers in diameter, or 100 to 200 atoms. It's not a single atom point, as sometimes is mentioned in the literature, often made out of an element such as a diamond, but a form of carbon, but basically at least it's incredibly tiny and incredibly sensitive, and it moves across the surface of a material and stays at a constant level above that material, so it goes up and down across layers of atoms, and through a computer can be imaged to show those changes in topography, if you like, going across an atomic landscape. In other scanning tunneling microscopes, the current is kept constant, and in an atomic force microscope, the force between the tip of the cantilever and the surface is kept constant. So either way, you have a picture of, at the atomic level, individual atoms. Atomic force microscopes can also scan at the surface level, and therefore they can also manipulate atoms at that level as well. And this is being used increasingly, as I mentioned before. It's being used to create the new type of quantum computers that we saw in a previous program. So that's one type of tool that's extremely valuable, and already new uses are being found for these tools. For example, very dense storage is possible if the atomic force microscope of that little cantilever tip, or tip that's attached to a cantilever, can be made to depress a polymer underneath it, create a tiny pit. You get incredibly dense methods of storing information. And then if you can aim a laser at that pit so that to melt that polymer and bring it back to normal, you've got a read-write capacity. Now at an individual tip level, that's not very fast or very efficient. But now arrays of these atomic force tips are being created, 1,024 in a grid-like structure, so that simultaneously it can read and write across polymers, for example, or other types of material. This is actually called the millipede, where it's being developed at the moment. So this is very dense storage. Again, we have quantum computers, very fast processing in parallel, using the superposition of quantum bits, quantum parameters of the atoms, individual atoms such as spin. And even further tools are being applied, such as lasers. Lasers are being used not only, of course, to be able to develop gamma rays, which are capable of changing the nuclear composition, ejecting neutrons, for example, but lasers that can manipulate transparent or semi-transparent objects, for example cellular objects, the vesicles in cells, because in a laser the central core of the laser has a higher intensity, the photons are at a higher intensity than the edges and create a differential, and can therefore be used to change the momentum of these tiny translucent objects, and in fact suspend them above the laser at a focal point as well. And again, you can create multiple laser beams using holograms, using certain types of holograms. So you can do all this in parallel. You can do it, you can manipulate using laser beams, particles, nanoparticles, thousands of times. So using lasers, atomic force microscopes, and particularly the new tools of biomolecular techniques. Now, at the biomolecular level in cells, of course, everything happens very precisely. It happens at the DNA level, at the protein level. It happens within cells, it happens between cells. But everything is very precisely organised, and engineers would love to be able to capture that organisation or leverage off that bio form of self-organisation that's evolved over millions of years. And they're beginning to do that because the first thing they want to do is develop a biomolecular transistor, for example, using nanotubes, the little tiny tubes made out of graphite rolled up, hexagonal graphite, for example, hexagonal structures, the new buckyball structures. So you've got tubes, you've got cubes that can be created, you've got little nano wires, and all these have to be linked. For example, if you want to create biomolecular transistors, they have to be linked to particles of gold, for example, electrodes of gold. But to be able to string these nanotubes between the electrodes, these tiny little cubes of gold or spheres of gold or silver, which can be maybe 5 or 6 nanometers across in themselves, same as when they're used for catalysts again. If you want to be able to do that and then put a voltage underneath so as to create a transistor, you must do it very precisely. And the way it's being done at the moment is to do this by attaching DNA to the ends of these tubes, patching them up into smaller tubes, and then be able to link with DNA. It does this very well. DNA is able to, through its nucleotide bases, be able to link to complementary bases and therefore attach very precisely, and this is what's being done. So at the end of the nanotubes, certain types of DNA, certain types of bases are being attached, and they're being linked to other DNA bases so that they're positioned precisely, much more precisely than can be done, or much more easily than can be done with devices such as atomic force microscopes. And as well as that, new types of tubes that are actually made out of viruses or bacteriophages, for example, can be applied. These form semi-stable structures or semi-firm structures which can duplicate nanotubes well. So actually using living organisms to create components of machines, to create components of semiconductors, for example, to be used for processing. This is being achieved in various laboratories now around the world. So there are some of the techniques and some of the tools that are changing the way that materials are being created. Viewers, we mentioned the application of nanotechnology to develop better and more sensitive and smaller sensing devices. This can be done by combining, again, biology with chemistry, with engineering, to link, for example, DNA particles to inorganic metallic particles such as little gold or silver nanospheres, nanocubes. It means that when the DNA links to the particular antigen or the particular molecule that's being evaluated, the inorganic metallic particles cluster together and change colour. So we see an immediate colour change when there is a link with the target molecule. That's one type of sensory device, and it's very sensitive. Very small amounts of DNA are required to achieve the result. But also more recently there's been some advances, not quite at the nano level, certainly though at the very close to the micro level, of tiny processes, tiny silicon particles, if you like, that can act as sensors en masse. Thousands, hundreds of thousands of these little sensory devices which can contain their own, in the future will contain their own processors. At the moment, the experiments are being done on at the millimetre and micrometre levels, but in the not too distant future, because again this field is roaring along now, and this is what this update program is about, because things have changed so rapidly even over the last year or so, at the nano level eventually. And these will be able to link in networks, if you like, vast networks around the globe to monitor for earthquake activity, changes in pollutants, for example, could be released into fires, wildfires, so as to track which way the thermal currents were blowing, which way the cinders, the elements of the fire were, the trajectory of the fire, if you like. Any difficult areas, it could even be released into Yucca Mountain, which has stored radioactive waste. Anywhere where humans would find it very difficult to go, these sensors can be released, and they can again form networks. They'll be an extension, if you like, to the internet, because they'll each be powered by solar radiation, for example, and be linked by radio, have little radio components so as to be able to link to each other for a small proportion of the time only if required. But we'll have intelligence, in other words. So you'll have networks of particles which have intelligence, and they'll act pretty much like a swarm of bees or a hive of ants. Their intelligence will be amplified by the fact that they will be constantly in touch, constantly communicating and disseminating their intelligence. We haven't talked much about the downside of nanotechnology. The fact that tiny particles can be released into the atmosphere, whether those particles are being used to develop cosmetics, or whether they're being used for sensors, or whether they're being released into the sea to act as markers there for various projects, whether to keep track of fish or keep track of, or if you like, sense when there's enemy vehicles, enemy submarines, whatever. These particles will be everywhere. It'll be very hard to keep track of them, very hard to keep inventory. And they can also disappear into the tracts of humans as well, and they'll be used there for medical purposes, of course. Tiny little machines at the nano level will go and fight antigens, will fight viruses, can be enlisted, in other words, to assist the current arrays of that are employed by the immune system to fight antigens in the body. So, however, it may be that some of these particles will be ingested accidentally and go to the wrong areas, whether it's inside a human or whether it's across the planet somewhere where they're not supposed to be. Either way, it'll be very hard to keep track of them. Also, the fact that eventually these swarms of nanoparticles may have intelligence, and intelligence can be greatly amplified in a swarm. For example, there was a great fiction book recently, it was published about a year ago, called Prey, in which these swarms of nano-intelligent particles preyed on live things, including humans. A bit of science fiction thrown in, but something that major scientists, including Bill Joy of Sun Corporation, their chief scientist, was worried about, and many others are too. The fact, if you combine nanotechnology with intelligence, with bioengineering, you could get a very, very potent brew, and one that may just escape, replicate, amplify, whatever, and it'll be very hard to put that so-called nano genie back in the bottle. So there'll have to be very careful track kept of these new technologies. Whether there will or not, I don't know, because the technology is going ahead so quickly. By the time you have ethical committees chasing it up, it's a bit like cloning or stem cells, it's happened. So whether we can keep control over these new technologies is another matter, and very, very highly contentious one at that. Viewers, we've only had time in this update for a very quick snapshot of this emerging, amazing technology that's going to reshape our society, and literally reshape it. We haven't had time to mention, for example, the new techniques in nanomanufacturing, using nanoparticles as a substrate that can be layered and, under the control of computer-aided design, build macro objects from scratch rather than have them machined. We haven't had time to look, for example, at the new techniques using very fine patterning, very fine lithography using atomic force microscopes to achieve those patterns. This is called dip pen lithography. Much finer than can be achieved with any of the current semiconductor techniques. We haven't had time to look at the new scaffolding techniques where shape-persistent viruses are used to act as scaffolds for inorganic materials, inorganic metals, and in liquid crystals as well. So there's a million applications. And what we see here is a convergence of many sciences, of course. All the sciences virtually are converging at this level. This new threshold that will allow us to basically manipulate, as I said at the beginning, all matter, all forces at that atomic and subatomic level. I'm David Tao, and you've been watching the Theories of Everything program. I'll look forward to seeing you again next week.